Okay. So since this is a graduate level class, I'm going to assume that you have mastered all of the material in real analysis. If you haven't, please do so. You can do that by talking to each other, reading the book, talking to me, or any combination of those three. Okay? But we do not have time to go into all of the topics in real analysis. I'm going to assume you know open sets, closed sets, convergence, limits. We need this language to attack real problems, to attack complex problems. Sorry, real complex problems. Okay? And the language of this is going to be extremely useful for the language of differentiability. There are several ways you can teach complex analysis. One way is Calc 3 heavy. Given the history I've had teaching classes with Calc 3 as a prerequisite, I am not that eager to do a Calc 3 heavy approach to complex analysis. So you will notice that there is a section in Chapter 1 which talks about Jacobians and talks about looking at these as maps of R2 to R2. I am not going to really delve into that approach. I want you to be aware that it exists, and if you're comfortable with your Calc 3, go back and look at that. If you're not comfortable with your Calc 3, you can, of course, review that. All right, so we talked about a complex number x plus iy. We know how to graph them. We know the complex conjugate is x minus iy. We have our definition of complex differentiability. So complex differentiable, often called holomorphic. And this means that the limit as h goes to 0 of f of z plus h minus f of z over h exists, and we'll denote it as f prime of z. So you always want to ask, is this good notation? Well, it's related to our function, which is good. The prime means somehow it's derived from it. The point z matters here. H is gone in the limit. It looks just like the definition of the derivative in real variables, except we've replaced x with z. The real difference is that we require the limit to exist along all paths. What this means is it's much easier in some sense to show a derivative does not exist than to show a derivative exists. How do you show a derivative does not exist?
Find a path that doesn't work.
That's one way. One way is to find a path when it doesn't work, but it could work along every path.
Find paths where they're different.
Find paths where they're different. So you either find one path where the limit doesn't exist, or you find two paths where you get a different answer and you're done. To prove a limit exists, you have to show no matter what path you take, and this is where we get, the paths like this. And when my kids were younger, I actually had the preschool classes at the Williams Children's Center make individualized scribbles for all of my Calc 3 students, to get this, and this is what you should always remember. So if you're yelled at for doodling in one of your humanities classes, say, I wasn't doodling, I was thinking about a limit from complex analysis. And if they have any issues with that, let me know. I'm happy to talk to them. All right? What function do you think we should take the derivative of, or try to take the derivative of first?
Just like
Yeah, constant, right? So step 1, f of z is constant. Trivial. I'm not going to bother doing that. But always start small, build up some examples, and move from that. All right. Building on a great example of the constant, what should we try next? Z. Now, with a little bit of work, you can show that all the rules of differentiation that you proved in Calc 1 still hold. The derivative of a sum is the sum of the derivatives. The derivative of a quotient is that messy expression. The derivative of a constant times the function is the constant times the derivative. Boom. Okay, we've now proved all those. You can see that nothing uses really anything other than the limit exists. So all those proofs translate immediately. If we take f of z equals z, then we get the limit as h goes to 0 of z plus h minus z over h. So this is the limit as h goes to 0 of h over h, also known as the limit as h goes to 0 of 1. This is probably the easiest limit we will study all year. Just 1. Okay, so that derivative exists. What should we check next? There's two natural choices for what to look at next. Yes? So one possibility is z to the n. And then I'm not going to bother doing it. It works very similar to the proof before. My question to you is, knowing that the derivative of f of z is z, can you actually get that the derivative of z to the n is n z to the n minus 1? So leave that as an exercise to see if you can actually get that. So that's one avenue to go to, is z to the n. There's another function we could look at next. The conjugate. So let's take I'll give it a different name. Let's give it a g of z is z bar. So this is the limit as h goes to 0 of z plus h complex conjugate minus z complex conjugate over h. So it's the limit as h goes to 0 of h bar over h. And now things get interesting. So if h is real, then the complex conjugate of h is just h, and we'll get 1. If h is purely imaginary, say h is I times a very small number, I epsilon, then h bar would be minus I epsilon. So this limit equals 1 if h is real, and it equals minus 1 if h is an imaginary number times a real number. So we found our first example of a function which is not differentiable. Is this a bad function? Why is it not a bad function?
I mean, it's one-to-one.
It's one-to-one.
I mean,
It's continuous.
yeah,
And if you viewed this as a real function, would this be differentiable as a real function? Do the partials exist?
yeah, the partials all exist.
The partials all exist. So this is not a bad function if we use that as our perspective. In terms of complex analysis, this is a terrible function because the derivative depends on the path we take. So there is a difference between real differentiable and complex differentiable. To be complex differentiable is an extremely strong condition. You do not want to prove every possible path gives you the same answer. You'll do nothing but check paths. There's too many paths to check. You need to somehow show all the limits at once. You need to be able to do some kind of general argument. Okay? Everybody happy with these? All right, so then the question becomes, this tells us there's only going to be certain types of functions that will be complex differentiable. And they're not going to just be the functions that were nice as a function of real variables. Somehow it's how the x and the y are amalgamated together matters. And we have basically two real data points. We have z and z bar. Now notice I can write x as z minus z bar over 2. And I can write y as, no, I want to do z plus z bar over 2. Because this is x plus iy, x minus iy, the y's cancel. And then I'll write y as z minus z bar over 2i. So what this tells you is if I give you a function in x and y, I can write it as a function of z and z bar. Or if I give you a function in z and z bar, I can give you a function in terms of x and y. I can go back and forth between these two perspectives. Woefully too little data, but things that are functions of z seem to be differentiable. Things that are functions of z bar don't. So as a rule from just one real example, if our function only depends on z, maybe it's complex differentiable. And if the function has any z bar dependence, maybe it's not complex differentiable. Dangerous from looking at too few data points, but as not everybody here has taken a class with me, if you've taken a class with me and you know the example, please don't say so. Can somebody tell me what 16 over 64 is in lowest terms? 1/4, excellent. 19 over 95, let's do a harder one. 1/5, okay. It's Monday morning, could be a long weekend. All right, how about 49 over 98? That's a harder one. Yeah, see, it's not so easy now, huh? 1/2. 12 over 24. I'm sorry? 1/4. Right? 16 over 64 cancels the 6s, I get 1/4. 19 over 95 cancel the 9s, I get 1/5. Right? 49 over 98. You never learned that if you have a ratio of two two-digit integers and the anti-diagonal elements are the same, you cancel the anti-diagonals and then reduce as needed? I've checked 3 examples. Sometimes you actually only check 2 examples, so if somebody's skeptical, you have a 3rd example in the bank. I think I've used all the examples I know. For the record, If I write here 1/4, that would be wrong. Okay? You have to be very careful. Just because you've checked a few examples does not mean you have found the pattern. But it doesn't mean it's a bad idea to check examples. So let's assume we have a function that is differentiable. So assume our function f of z is differentiable. The further you go in mathematics, the more willing you are to abuse notation. Okay? So when I write f of z, I'm writing a function of a complex variable. A lot of times people will often write in a very annoying way, f of z is a function of x and y as well. And this is technically not the same f as this. Okay? Usually it's clear from context what's going on, and very rarely do students revolt and charge the professor. I was in a class where they had f's on the left and the right-hand side of an equation, but the right-hand f was not the same as the left-hand f. That crosses a line for me. When you're at that point, that's too much. But for something like this, I have a function, and I can regard it either as a function of z or as a function of x and y. Think of it as we've generalized the absolute value notation, and now it's not just the absolute value of a number, it could be the absolute value of a vector as its length, that we allow it to act on more things. So if I write it like this, it should be clear from context. And then I'm going to write it as a function of u of xy plus iv of xy. And the reason is f is a function that takes complex numbers to complex numbers. So f is from c to c. And so you give me an input, my output has to be a complex number. Let u of xy be the real part of that complex number. Let v of xy be the, it's not, this is just a definition right now. The question now becomes, what u's and v's are possible if I have the requirement that my function be complex differentiable? Well, this is the second day of class, first real day of class. We haven't done that much. Only thing we've done is we've done the limit. And we've talked about how when we have a limit, it has to exist for every possible path. There are certain paths that are more natural to look at than others. Right? What are our two go-to paths? Yes, and I was hoping somebody didn't go like this. Yeah, you can go vertically, you can go horizontally, the axes. Right? So what we can do is we can look and see what happens if we go along those two paths. So f prime, and it's always a question, we'll do it at the point, say, xy. And then this is now dangerous notation. So this should be maybe the limit as h goes to 0, h is real, just to remind ourselves, of f of z plus h minus f of z over h. And so since h is real, I'm just changing the x, I'm keeping the y fixed. So this is going to be the same as the limit as h goes to 0 of u of x plus h y plus I v of x plus h y minus u of xy minus I v of xy all over h. Just trying to make sure it stays focused. Okay. So when you see something like this, you want to group things. I've got a u of x plus hy, a u of xy. Those two want to group together. These two want to group together. And what is u of x plus hy minus u of xy over h? Yes. That's the partial of u with respect to x. So when we now simplify this, we now get that this is equal to du dx, that's the first one, plus I dv dx. Right? So that's one way to calculate it. The other way is it's the limit as h goes to 0, h is purely imaginary. There's other paths I could look at as well. I'm choosing these two. All right, so if I look at this, I will then have, same as before, I'm not going to bother to write f of z plus h minus f of z over h. Let's just go straight to the fun stuff. We'll have u of x. Now it's going to be y plus h plus IV of x, y plus h minus u of xh, I'm sorry, x, y minus IV of x, y. And divide this by what? So we've got to be careful. So is there a mistake in what I've written so far?
Oh.
Very, very easy to make mistakes in the subject.
Yeah, it should be y plus h should be y plus.
So let's write h as I times k. So a lot of people prefer not to have your variables. If you know they're negative, pull out the negative sign. If you know it's imaginary, pull out the I. You know what they say about complex analysis? It's a really bad joke. It's only fun until someone loses an eye. So we'll write this as y plus k, and then down below it's ik. Ah, that makes a huge difference. This is no longer du dy. It's du dy, but we have to divide by an I. So we're going to get here, so can people still see down below? We get negative I du dy. And now the i's actually cancel, and we'll get dv dy. Okay, well, now what we can do is we can just say, well, look, we have two things that are equal. Let's just equate the real parts and equate the imaginary parts. So we get the real part, du dx equals dv dy. And then the other one is we have dv dx equals negative du dy. Or I could, of course, write du dy equals negative dv dx. Sometimes they're written more concisely as u sub x with a partial v with respect to x equals vy, and maybe the partial v with respect to y is negative partial v with respect to x. That's the more concise way. So these are called the Cauchy-Riemann equations. So a lot of this semester is going to be a race to see who has the most theorems, Cauchy or Riemann. This one is kind of a nice one to start with because they each get on the board. What have we shown here? What did we just prove?
If f is differentiable, then...
Okay, so if f is differentiable, then the Cauchy-Riemann equations hold. What would you like to be true?
If and only if.
If and only if. If the Cauchy-Riemann equations hold, then f is differentiable. So the question is, do the calculation every single time by looking at every possible limit. By the Cauchy-Riemann equations, if we want to prove something is differentiable, all we have to do is check, is the partial v with respect to x equal to the partial v with respect to y? Is the partial v with respect... That's very easy to do, at least relative to looking at all possible paths. So you get a sense of why this is such an important theorem in complex analysis. This is a really good test. If you think back to Calc 3, you can think about the definition of the directional derivative versus the formula to compute the directional derivative, and just how you want a good way to calculate things. And then you can define certain types of operators. So we have plenty of time. So we're looking at the various stuff over here. And so we can define some operators. We're going to define an operator d by dz and d by dz bar. And they're going to be related to d by dx and d by dy. We're going to try to find a way to combine them. Okay? So again, we can define a lot of different things. The question is which definitions are going to be useful. Now we know the Cauchy-Riemann equations hold. So what does that mean? It means du dx minus dv dy equals 0. dv dx plus du dy equals 0. What's the hardest part in remembering the Cauchy-Riemann equations? What's the most difficult part? Which one takes the negative sign? How can you easily either remember or quickly rederive which one takes the minus sign? I mean, one thing is, of course, to just reprove it. Which one needed the I to be drawn out? One thing you can do is, let's say you have a relationship and you know it up to a sign. Choose a special function. What function should we choose? Okay, so if we choose the conjugate, the derivatives are going to be 0. So we might be bad there. I would choose a function that's differentiable. Now, if you choose the function z, z is x plus iy, that's too easy to work with. Because, du dy is 0. And dv dx is 0. So if we try that, the function f of z equals z, it's not going to suffice to remember this. So what function should we try? So z is too simple. Z squared. Right. So if you take z squared, you get x squared plus y squared plus 2ixy. Now u and v really both depend on x and y. And so now if you check just the function z squared, that will tell you which way the sign goes, and that will tell you what the Cauchy-Riemann equations are. So this is a good thing in life, is sometimes you only have to remember enough to get the rest. Have you ever heard of the sonnet password scheme? A lot of people, when the internet was young, you had to have strange, no special symbols, no numbers, but you had to have a certain length. And sometimes length had to be long. And a lot of people would use the first letter of each line of a sonnet or a poem. Do you have to remember the whole sonnet? No. Do you have to remember the first line or the first word of each line? What's the only thing you have to remember? I'm sorry? Well, let's say you forget the letters. What do you have to remember to figure it out?
The name of the sonnet.
The name of the sonnet. So let's say your poem is Death Be Not Proud. All you have to remember, oh yeah, it's Death Be Not Proud. So then you can just look up and then figure out the rest of it from that. Whenever possible, you want to have little markers to remind you. Okay, all I have to do is this, and then I will be fine. All right, so what I want to do now is I'm not going to prove the other direction. I'm only proving half of the if and only if. The other half is about a paragraph of algebra in the book, and so I will leave that to you to read. Okay, and so now what I want to do is I want to define my operators. I want to make sure I do it right. I will have d by dz is going to be 1/2 d by dx plus 1 over I d by dy. And d by dz bar will be 1/2 d by dx, and I believe it's going to be minus 1 over I. Yes, minus 1 over I d by dy. Okay. One of the painful things in complex analysis is 2's and z's look a lot alike. So I will always try to put a slash through the z. We're not dividing by z here. Okay. Let's see what happens if we apply d by dz to the function u plus iv. Well, that's then going to be 1/2. We'll have du dx plus 1 over I d by dy of x plus 1 over I du dy. So that is what happens when the d by dx hits u plus iv. Now the 1 over, I'm sorry. It should be I plus I, du dx. Right? That's what happens when d by dx hits u plus iv. We get du dx plus I dv dx. And that was not erased well. Now we have to have the 1 over I d by dy hit thing, so we'll get plus 1 over I d by dy of u, so it's be du dy, plus 1 over I. Oh, but now we have an I over here, so that cancels, and we will get dv dy. So let's look at the real part. We have du dx, and we have dv dy. What do we know about du dx and dv dy? They're equal. And so this is then going to just be du dx. What about I dv dx and du dy? What about dv dx and du dy? They're opposites. So this will just become plus I dv dx. And this is why we had to put in the factor of 2. I'll leave it as an algebra exercise to go through and see what would happen if you applied d by dz bar. What would you guess if you applied to a function that satisfies the Cauchy-Riemann equations? What would you expect to get? Yes?
Probably that thing except with a minus sign.
So would you get that thing with a minus sign?
Would you get 0?
So which do you think? Do you think you'd get this with a minus sign, or do you think you'd get 0?
Oh, yeah.
Maybe we should do the calculation. So this is the power of being at the blackboard. I put a bar over this with chalk. And so now, is there any change in the first part? No. And the second part, all that changes is this becomes a minus sign, and this becomes a minus sign. So whereas before everything reinforced, and I got 2, now I get 0. Or if you want to do it really pedantically, 0 halves rather than 2 halves. Ah, so when I apply the operator d by dz bar, if my function is complex differentiable, it's 0. So that's a nice lemma to isolate. Lemma. If f is holomorphic, then df dz bar equals 0. Okay. If the blackboard space is too compressed and tight here, let me know. We can actually rotate the classroom 90 degrees if people want. Okay, but we will not do that in the middle of the lecture. Okay. These are extremely powerful operators. If you go further in mathematics, d by dz and d by dz bar combine. Have any of you seen like the Poisson operator? Or okay. It's always interesting because I know we've had some partial differential equations classes at Williams in recent history, and I know some people have looked at stuff like that. And so if you've seen stuff like that, I want you to at least be aware of the stuff. Okay, so I think now it's the Calc 3 part of the lecture. Ah, yes, it is the Calc 3 part of the lecture. Okay, so I want to at least mention Stokes' theorem a little bit and talk a little bit about why it's true and how it's useful. And again, one of the great secrets in Calc 3 is that early in the semester, if you're giving students path integrals to do, frequently those are path integrals that can be done much faster with Green's theorem, which the professor knows and the student doesn't know at that point. So we can easily check and see if the answer is right. So what is Green's theorem? Does anybody remember the statement? So we'll have some function, the integral over some region of dq dx minus dp dy is equal to the line integral along the boundary of the region of p dx plus q dy. I'm pretty sure I got it right. It's dq dx, I'm pretty sure, yes. Okay, this is Green's theorem. If you want a quick proof, we got time for a quick proof. Okay, what are the good shapes for calculus, for integration? Rectangles, right? Especially if you're doing, Calc 3, if you're doing a two-dimensional object, you want rectangles. What's the whole point of spherical coordinates, or polar coordinates, or cylindrical coordinates? You basically convert a sphere to a cube, or a box. In polar, you convert a circle to a rectangle. And we can integrate over rectangles very nicely. Then you have this weighting function, that's the Jacobian. But the whole point of all these change of variable formulas in Calc 3 is I can integrate over rectangles. Frequently, you have a choice. Would you like to have a really nice integrand and a really painful region, or a painful integrand and a really nice region? Typically, nice region trumps nice integrand. Okay, so now why is this true? Well, let's say I give you some region. What I'm going to do is I'm going to divide it up into a lot of boxes. Then you have to be a little bit careful as you get onto the boundary. Okay, so I'm not going to worry about what's going on the boundary. This is where professors earn their paycheck, by actually proving rigorously that you can deal with the boundary issues. If not, imagine your region over here is a bunch. It's like some kind of grid. Then if it's a grid, then there's no problem in making the rectangles. And then you can take the limit, and as you take the limit, there's really going to be no difference between an area integral over a rectangular region like that and the actual smooth curve. So let's take a bunch of rectangles now. We're doing a line integral, so line integrals are oriented. Do we go clockwise or counterclockwise? Always counterclockwise. So in this one, we travel it like this. In this one, we travel like this. In this one, we travel. You see how easy it is to fill up a 50-minute lecture? So you keep going like this, and what you notice is all the interior walls cancel. And so when you do these line integrals, the line integrals actually internal walls cancel, and it just propagates out to the boundary. And so in some sense, if we can prove Green's theorem for a rectangle, we know Green's theorem everywhere. So all we have to do is prove Green's theorem for a rectangle. So the question is, do we want to start off with the double integral and try to get to the line integral, or vice versa? Well, let's start off with the double integral, dq dx, dx dy, dp dy, dx dy. You have a 50-50 chance. For dp dy, do you want to integrate with respect to y first or with respect to x first? Do you want to find the antiderivative of dp dy with respect to y, or the antiderivative of dp dy with respect to x? If you phrase it clear enough, the answer is screaming at you. I want to find the function whose derivative with respect to y is the derivative of p with respect to y. I think I can find that function. Right? And then since I'm going to be evaluating it at boundaries, I don't have to worry about finding an arbitrary function. I don't have to worry about the plus c. Right? So what function will I take as the antiderivative of dp dy with respect to y? I'll take, sorry? Y? Why do I want to do this? I want to find what function is the antiderivative of dp dy with respect to y. P. Right? So if you look at this, let's say here's our rectangle. And this is the point maybe AC, and this is the point BD. So this would be the point BC, and this would be the point AD. So I need to integrate dp dy with respect to y. So what I'm going to do is I'm first going to fix a value of x, and then I'm going to integrate like this. So the double integral of dp dy. So y is going to go from c to d, and x is going to go from a to b. Even though I do not have nearly enough chalk in this class, I guess there's some pieces there, good. Even though I don't have much chalk, I think it's a good idea to waste some and clearly write down what are your variables in your integration so you don't confuse the orders. So dy and then dx. So I'm going to now get the integral x goes from a to b, and so I'll get p at the point x, and then I'm going to have at d minus p at the point x, c dx. Right? I have a negative sign, so then that makes this one negative and this one positive. And now look at what I have. I have the positive integral of p xc. That's just the integral along this piece. What's the integral of p dx as I go up here? That's just 0, because x is not changing along here. Over here, I've got a negative sign. I'm going backwards. So this piece over here, this is just the integral over the boundary of the region of p dx. And then you just do a similar argument for dq dx, and that's going to give you the q dy term. And so this proves Stokes' theorem. Okay? And you have to just do some work for the boundary, but all right. People happy with Stokes? There's, of course, more than Stokes. This is technically in the plane, it's often called Green's theorem. The higher versions are called Stokes' theorem. And what's really going on is you have a region, a boundary, a function, and an antiderivative. The most general way of writing this, so it's just worth seeing this, generalized Stokes. You really need differential forms to write this correctly, but the integral of omega over the boundary of some region is equal to the integral of d omega over the region. Essentially, this is the fundamental theorem of calculus. And you can think about the integral of f prime over an interval is now the antiderivative at b minus a, basically the value at the boundary. So the fundamental theorem of integration is basically passing the derivative operator from the function to the region. And the derivative of the region is essentially the boundary. There's a lot of great mathematics behind this. Okay, we want to apply Green's theorem. And we have stuff about these nice integrals. So we can consider apply Green to our function. So we have f of z is u of xy plus I v of xy. Okay? So, all right, so I'm going to do it like this. Okay. There's a couple of ways you can do the calculation. I want to do the same way that I've posted in the notes. What do you think dz should be? So f is u plus iv. What do you think dz would be? Z is x plus iy. What would you say dz should be? Dx plus I dy. Good. If this seems a little fast, just put on a physics hat or an engineering hat. We will justify and make all this rigorous, but this is the quick proof of why we will get what we get. Let's look at the integral along some closed curve of f dz. All right, well, this is the integral along a closed curve of u plus iv dx plus I dy. This is going to be the integral along a closed curve of u dx minus v dy plus the integral along a closed curve, and I'm going to pull out the I. We'll have v dx plus u dy. Okay? What should we do now? CREqsGreensThm, right? Green it. All right? You basically can take anything and turn it into a verb. One of my thesis advisors said the most important verb is Cauchy-Schwarz. You Cauchy-Schwarz the... So when we apply Green's theorem, P is equal to U, Q is equal to negative V. We've got to be very careful. So this is the double integral. So Q is negative V, so we get negative dV dx. And now P is equal to U, so we get negative du dy. And then over here, P is equal to, okay, now Q is equal to U, so we get du dx minus dV dy. Right, now what do we do? Yes, there was a reason why I've been compressing myself to this side of the board for the last, 50, actually we can check later, 15 minutes or whatever. I want the Cauchy-Riemann equations to stay on the board. Right? All right, what is negative dV dx minus du dy? 0. What is du dx minus dV dy? So this equals 0 by the Cauchy-Riemann equations. So what we've just proved, and this is like a physics proof, what we've just shown or suggest is that if you take a function which is differentiable and integrate it along any closed curve, you get 0. Now we're going to be a little bit careful about what do we mean by differentiable. I don't mean differentiable just on the boundary. I mean differentiable inside, and maybe to be safe on a small epsilon neighborhood pushing past the boundary. This is a remarkable result. It's basically telling you all these different integrals are 0. When I taught Calc 3 at Princeton, I took a coat hanger and I taped a plastic bag to it. I think it's still in my office. And I would move my hand in the plastic bag. And because the boundary of the curve didn't change, all the surface integrals were the same. This is even stronger than they're the same. They're all 0. So let's think back to Calc 1. Are most integrals in Calc 1 0? There is a class of integrals in Calc 1 that are always 0. Anybody know which integrals in Calc 1 are always 0? What interval do you want to integrate over? Yeah, the interval at a point. I'll let you try to figure out what BFD stands for. The integral from a to a of f of x dx equals 0. This is not a momentous statement. But let's think geometrically what's going on. Please describe all closed curves on the real line. They just point. Now, I could go at a point, go off, and come back. But because I traverse this in opposite directions, it cancels. I could go back and forth like this 2015 times. It's essentially equivalent to just a point. So when you consider what kind of closed curves you have to look at on the real line, it's boring. Geometrically, the real line just isn't that interesting. And we saw this when we were looking at differentiation. It's not that strong of a condition to be differentiable. In the complex plane, things are very different. Can you give me a closed curve in the complex plane that's not trivial? Circle. So in the plane, geometry of closed curves is a subject. This is not a subject. This is an observation. But now, I could have an obstruction, in fact, if I wanted here. And I could have a closed curve that goes around the obstruction. So you could have a function that's nice except at a point. And then what we would often do with GreensThm is we would draw another curve around that, and then we would say inside this annular region everything is fine, and then the integral over the outside circle is equal to the integral over the inside circle, and then you reduce things to integrating over small circles about points that blow up. That's what complex analysis is all going to be about, is reducing things to integrals of things that blow up, and you're just going to integrate in a circle around it. So because of GreensThm, we're going to essentially reduce to all of this. Now, what I did was not a proof. What the hell does the integral of f dz mean? Let's just play with some symbols, we've got some time. But it is highly suggestive of what we're going to get. So the geometry here is highly non-trivial. As an aside to prepare you for later this semester, what happens if we go to functions of two complex variables? What does the geometry look like there? Most of us have trouble visualizing four-dimensional objects. This is a very hard handicap when you're teaching complex analysis because the graph of a complex valued function which maps c to c, you need 4 dimensions to look at it. So people often do things such as color shading, or they plot the absolute value. It's a lot of different tricks to try to give you a sense of what's going on. But the whole point is we are going to be able to use non-trivial geometries to convert a lot of painful integrals to just algebra. And all we will have to do is integrate over circles. Okay? So this is the big point I want you to get from GreensThm and from what we've been doing before. If you think about the functions we apply GreensThm to, the ones we love the most are the ones where dq dx minus dp dy is 0, because then the integral is nice. There's actually another function that's worth applying to, and this will be a good place to stop. So Stokes is q sub x minus p sub y dx dy is the integral of p dx plus q dy. And here's the integral over the boundary of the region. Here's the integral over the region. There's a really good choice for your function p of xy and your function q of xy. Does anybody know the choice people often like to use to get something really nice? So one thing is, I could have q sub x equal p sub y, and then you're just integrating 0. But if I want to have something non-zero here, what would be a good non-zero number to have? 1. If I have 1, what do I get? I get the area. So if I take p of xy to be 1/2 y, and I take qxy to be 1/2 x, then over here, I get a very nice line integral that gives me the area. So you can actually get areas of regions by doing appropriate line integrals.
We want minus 1/2 y.
Probably. Yes. So if you put in the correct function, you can get the areas. Then, of course, it comes down to, can you actually do the line integral? What would be a good shape to try this on? Circle. So as a nice exercise, see if you can get either from the area of the circle, the perimeter, or from the perimeter of the circle to the area. And as an aside, you should think about the relationship between differentiation and the area perimeter, as well as for a sphere, volume, and surface area. Okay, good place to stop.